And so here's the title, Roving in the Deep, or ROVing in the Deep, exploring the Challenger Deep Forearc segment in the Southern Mariana Trench with Jason Medea. And let me know if you can't see it, but I hope you can. And it's a lot of people put a lot of effort into this, so I'm just going to say the TN 438 Science Party, but many universities. So we're going to talk about the Mariana Arc, which is the southern part of the Izu Bonin Mariana IBM convergent plate margin, which can be traced from near Tokyo, Japan to south of Guam, USA to where the Challenger Deep is. So, and the IBM Trench marks where the Pacific Plate subducts beneath the Philippine Sea Plate. So here we're looking at the seafloor around the Mariana Island Arc and Trench, and in particular the Challenger Deep, which is a focus of a lot of work, especially Chinese in particular have been doing a lot of work there recently. But you can see it's a very interesting convergent margin. It's basically 1,000 kilometers north to south, and you can see the parallel elements. This is a classic convergent margin, intraoceanic arc convergent margin. So the Mariana Trench, there's Guam. This is the Mariana Arc, which consists of a structural high here and then a magmatic arc volcanoes up here that can be traced all the way up. And you notice that the magmatic arc, these big volcanoes kind of peter out around Guam. And we have the Mariana Trough, which is a very confusing name because it sounds like the Mariana Trench, but it's completely different. It's a back arc basin. It's actively extending zone of seafloor spreading. It's the best, it's the only active seafloor spreading segment that we have in the Northwestern Pacific. And then the West Mariana Ridge, which is an extinct remnant arc that was left when the Mariana Trough started opening about 5 million years ago. And this is all dead. It's just a structural high. And then we get into the rest of the Philippine Sea Plate, the Parissa-Beagle Basin. And then, of course, the Challenger Deep is down here. It's easy to remember because it's 11 kilometers deep at 11 degrees north. So we're going to zoom in here. Here's the Challenger Deep. Here's Guam. Here's these elements we were talking about. There's a little arc volcano here, and that's kind of the last big one we see. And then here's the West Mariana Ridge, the back arc basin, opening at about 47 millimeters per year. We know that from GPS. And so this is what we call the Challenger Deep Forearc segment, or CDFS. And this is what we were studying. It's about 600 kilometers. The eastern limit is well defined by the Santa Rosa Bank Fault. And then it seems to consist of two sort of arcuate segments, the eastern CDFS here, western CDFS here, which can be, continued until this 90-degree turn in the trench at the Yap Trench. This is 600 kilometers long segment. So this was a very international group, 8 research scientists, several postdocs, 8 graduate students, an undergraduate, 1 observer from the Marianas, 1 onshore, me. There were 4 nations involved. And it was aboard the research vessel, the Thomas Thompson, which was out of the University of Washington. We call it TN 438. And it was in late November, early December of last year. So Jason Medea are an ROV system that designed and built by Woods Hole Deep Submergence Lab and funded by the U.S. National Science Foundation. And the Jason Medea is a 2-body ROV system. There's a 10-kilometer reinforced fiber optic cable, which delivers electrical power and commands from the ship through Medea and down to Jason. The Medea is slightly shallower than Jason. It serves as a kind of a shock absorber, buffering Jason from the movements of the ship, and then also gives a lighting and a bird's eye view of what the ROV is doing beneath it. And this system can work to a maximum depth of 6,500 meters. So we had 10 dives. We were a little bit challenged with the weather, but we had 7 of them in the Challenger Deep Forearc segment. So you can see them here. 3 of them were up here, and the other 7 were down here. So we had 3 dives in the Western CDFS and 4 dives in the Eastern CDFS. And you can see the 4 dives in the East are J2. That's for Jason, 1670, 1677, 1679, 1678. So, and then the 3 over here, 1674, 1675, and 1676. So let's talk about what we saw in Eastern CDFS dives first. So we went down to what's called the Shinkai Seep, and it's been the study of Japanese research since we accidentally discovered it in 2010. And what's interesting, it lies, as you can see, at about 50, 57, 58, 5,800 meters. It's well below the carbonate compensation depth. So calcite, any kind of carbonate is unstable. And you can see these are different venting sites, and these are the area of the sites, less than a square meter, greater than 10 square meters. And these are different tracks by the Japanese man-submersible Shinkai 6500. So you can see it's quite a bit of work has been done there. Let's look at a short video about what we found there. There's no sound. I'll just narrate. But you can see here, there's the depth. Those are some of the hydrothermal, if you want to call them that, constructions. These are white. These are not like your normal high temperature hydrothermal vents. These are low temperature, and the venting, you can't see it. And in fact, you only know it's there because these things are continuing to be built in spite of being so far below the carbonate compensation depth. And you can see there's biology on there. Now, this was in 2019, and you can see the very fine structures on top of that. That's a suggestion that the structure is still venting when they have that fine serrated nature. Lots of tube worms growing on it. And you can see some other of these structures are not so fine. They're actually kind of smooth. And this will be important when we talk about how these things evolution. So here we're looking at 1 year. So here we're going to take a little fragment, and we will leave that there after we sample it. And then we come back a year later, and you can see what has happened. That's how much growth has been on one of these vent structures in 1 year. So it's not much growth. But it's definitely there. So here's another one. We took off this little thing in the middle, and you can see what grew in basically a year since then. So you can learn more about this in that paper in G-Cubed. So what we found is that there's 3 types of chimneys here. Very interesting. So where you have a high fluid flux, and it's not very high, you have these very fine structured chimneys, which are basically dominated by brucite. Brucite's a magnesium oxide carbonate that basically is what forms when the chimney is active. And then as the activity wanes, the brucite turns to calcium carbonate, but in particular, it turns into aragonite. And the aragonitic carbonate is slowly After the entire vent stops venting, then the aragonite turns into calcite, which is slowly reabsorbed in the seawater. So we have this extremely interesting evolution of chimneys in response to fluid flow through them. And if there's any questions, I'll respond to them, but somebody will have to tell me about them. All right, now not too far. This is where we went. We went there because we wanted to recover some sampling device the Japanese had put there 8 years ago, and that's why we dove on Shinkai Seed twice. And also, it's good to see because this is the only one we know about in this region, but there certainly must be more of them. We just haven't found them. They're very difficult to find. You have to stumble on them. Now, one of the things that we did over several years was to start to look at the rocks in this inner slope above the trench. So we did this traverse at about 143 north, I'm sorry, east, right about here. And you can see there's any number of dives, right? That the 6K is the Shinkai 6500. So that's dive 1363, 1364, 1431, 1432, a couple of years in there. And these are all of the samples that we got that allowed us to put together some kind of a lithologic structure cross section in here. So in green, we have mantle rocks, peridotite. In this blue, we have mafic intrusions in the upper part of the mantle, and then in brown, we have the crust. And in a few places, we found some very young basaltic breccias that are very interesting because they imply that there's igneous activity down here as well. In addition, we found some samples that we could date. So in one place, we found a 25 million-year-old hornblende garnetite. At first, we thought it might be an eclogite from the subduction zone, but then after doing the metamorphic petrology, we discovered it was a high temperature, high pressure, not something from the subduction zone, something else. And then the Shinkai seep field is about here. And then we also found some diorite and tonalite that we were able to date from about 46 million years ago up here as well. So very interesting section. But you can see we're only looking at part of the crust in here. There's a lot more work to be done. Now, during the TN 438, we did another dive, not far away from 143. 143 is here. This is just over here, a little bit to the east. And we found more peridotite. So this is fairly fresh peridotite. You can see the olivines in there. And these are the typical outcrops of these mantle rocks in the inner trench wall. So it looks like what we're seeing here is a crustal structure with the arc lavas sort of with the, on top, and then arc and bonanitic lavas down to about 5,000 meters, and maybe some plutonic rocks. And then this seems to be the moho. So the mantle crust boundary seems to be exposed in the inner trench wall at about 5,800 meters. And then just below that is the Shinkai seep that we saw. And then we were looking at various things down in here in that profile. But look at how much of the rocks have not been explored. We need something that can go deeper than 6,500 because for both the Shinkai 6,500 and the Jason Medea, 6,500 meters is the limit. So the hope is that we can work together and find a way to explore this slope at depths greater than 6,500 meter with the only tool that's capable of working at such depths, Ndouche. So now let's consider what we found in the Western CDFS. So as you recall, this is about the boundary between the Eastern CDFS, which seems to be dominated by mantle and older crust exposures with some igneous activity. And we don't know very much about what's in the Western CDFS. So let's take a look at these dives, 1674, 1675, and 1676. So this is a 1674. It's a, it's a very interesting breccia. In fact, we call it a double breccia because you can see these fresh, large chunks of probably basalt have been brecciated and turned into this light green pyroclastics. And then this breccia was in turn brecciated and turned into a new second breccia by this creamy matrix. So we found that at dive 1674. At dive 1675, we found other breccias. This one, you can see the fresh basaltic material, and here it's been brecciated with a very dark brown matrix separating the fresh black basaltic material, and then this creamy matrix that makes a second breccia, another double breccia from this dive. And then from 1676, we have an interesting sort of yellow thing where this matrix is very finely brecciated. And here we can also see that these rocks are in place because we have this kind of a slabby seafloor, that's a 10 centimeter difference between those two dots. And this very regular geometric shapes, and we interpret as cooling fractures of this pyroclastic material after it's settled on the seafloor and cooled. So this entire CDFS is a very different kind of a convergent margin than what we see farther north. This is up in the Marianas at 17 or 18 degrees. And here we see what you normally see with a trench, a forearc. We've got some serpentinite mud volcanoes in here. No igneous activity in here. It's underlain by cool serpentinized mantle. And the volcanic arc marks where the asthenospheric counterflow allows temperatures high enough that water coming off a subducted slab can interact to generate melt. And then the back arc basin right here behind it. That's kind of your normal situation for a convergent margin. There's the plate convergence vectors. Down here in the south, you notice immediately this forearc is completely different. There's no well-developed magmatic volcanic arc. There's something that looks like an incipient arc being developed here. And there's the back arc basin spreading ridge. So it's a very different situation. And what's interesting is in the case of your normal situation, you've got cold serpentinized forearc material preventing asthenospheric influx into this region, so you can't have melting. But in the CDFS, there is no such barrier. For reasons that we're still exploring, there's igneous activity right near the trench. So the Earth's mantle produces basalts at 3 tectonic settings: mid-ocean ridges, hotspots, and arc basalts. And arc basalts contain a lot more magmatic water than these other tectonic settings, but probably the Western CDFS magmas were very hydrous as well. And that has, these often erupt very violently because they're erupting and releasing the volatiles in them at low pressures. So these subaerial and shallow water eruptions of arc magmas in low pressure environments are typically quite explosive. But these deep water eruptions cannot be so explosive because they're erupted into high pressure environments. But we know very, very little about these because number one, we've never seen one. And number two, we're not exactly sure how deep this kind of igneous activity occurs. So here we're looking at what we know about pyroclastic rocks. So these have been studied from mid-ocean ridges and associated places by these authors. And these are showing the depth intervals at which they have that. Here we're looking at the critical pressure for CO2 and for H2O. And you can see that the things that we're diving on are occurring down here way deeper than anybody has been able to do. And what happened was in in low pressure environments, the magma comes up and it interacts with a low pressure environment and it erupts and you have water vapor driving the pyroclastic eruption. But this ultra deep sea volcanism is coming up and is intersecting the supercritical phase, so that the exsolution of magmatic volatiles is going to be fundamentally different. So TN 438, we sample the deepest known pyroclastic eruptions. These must be some kind of a supercritical pyroclastic eruptions, but there may be deeper ones. And that's one of the things that remains to be established, is how deep does igneous activity happen in the Challenger Deep Forearc segment? So TN 438 provided an excellent overview of the Challenger Deep Forearc segment, but left us with many unanswered questions. First of all, is the eastern CDFS mostly this old crust and upper mantle? Where is the moho elsewhere along the CDFS? A third question is the western CDFS mostly a young volcanic construction? Another question is, how deep, how close to the trench is the limit of CDFS volcanism? Are there more Shinkai Seep type vent fields on the CDFS, and how do we find them? Are there ultra deep high temperature hydrothermal vents in the western CDFS? If there's ongoing igneous activity there, there could be some ultra deep high temperature hydrothermal vents, which would have a completely different biology and fluid chemistry than those that are associated with mid-ocean ridges. What rocks are exposed in the CDFS below 6,500 meters? What vertical variations can we find in the upper mantle beneath 6,500 meters? And then finally, we would like to know if there are any subduction zone related imbricated metamorphic rocks present in that inner slope. So there's lots of work to be done. And thank you so much for listening to me. And if there's time, I'll take questions.